Welcome back, everyone. You ready for some more polynomial functions? Well, this might be a long one, so you might want to hit pause and get yourself a drink or a snack or something and come right back. Well, if you stayed here or came back, we're going to start with something simple, the factor theorem, and have no doubt about this. This is one of the cornerstones of everything we've got here. Let's see, where's my pen? All right. There we are. Okay. Ready to go. All right. Factor theorem. Pen's acting strange, but all right. Oh, there we go. All right. So we start with the polynomial for the factor theorem. The two things to remember and link together are that x minus k is a factor of the polynomial. That means you could divide it into it and get a remainder of 0. That and the fact that if you put that k into the function, you get 0. In other words, it's a 0. It's a solution. It's a root. And x minus k is a factor. Those two mean or work in the same way. So link those two concepts together, and there's your factor theorem. Now we're going to check and see whether x minus 1 is a factor of each polynomial. We'll have a couple of examples here, and let's see how we go. Okay, notice we've got 2x to the 4th here. So if x minus 1 is a factor, and that's what we're trying to find out, then f of 1 will be 0. So we're going to use synthetic division. We'll practice there. Remember, we talked about that last time. So here we go. Remember synthetic division? Just as a reminder, when you have x minus 1, the 1 goes here, not minus 1, 1. These two signs are different. For synthetic division, you need the 1 here. Now, remember, you bring down the 2. Don't touch it, just copy it. Bring it straight down. And take the 2 times the 1 here and put that number there. Now, all you have to do is add. You get a 2. Take that 2 times the 1 up here. There's your next product. Add these two together. You get a 5. 5 times 1. That goes here. Add those two. You get 0. And 0 times 1 is 0. But add it, and you get a 7. So that tells us two things. Well, first of all, it tells us f of 1 is a 7. Number 2, it tells us that x minus 1 is not a factor of f of x. And by extension, because of that theorem we just talked about, that means x minus 1 is not a factor of this polynomial that we've got up here. Moving on, we'll look at this one. We are talking about x minus 1 again, and we're going to check it against this one. So we bring down our 1, which is the opposite of the minus 1 we see here. Bring the 3 down, multiply it times the 1, bring that result over here, add those two, and there's your next number. Take the 1 times the 1 over here. That gives us 1. Add those two 1s, and you've got 2. 2 times the 1 gives you 2 here. Add down, you get a -6. -6 times 1 gives you the negative 6 here. Add, you get a negative 1. Negative 1 times 1 is negative 1. Add those, and how about that? We've got a remainder of 0. That not only tells us that f of 1 is 0, but it also tells us that x minus 1 is a factor of that polynomial up there. Oh, by the way, I failed to mention that. Notice that this is x to the 5th up here, so it's a 5th degree polynomial. If we divide x minus 1 into that, what we get is actually listed right here. Because when we do synthetic division, if the remainder is 0, this is the constant term, hence negative 1 down there. This is the x term, so you see negative 6x there. This will be the x squared term, so it's there. This is the x cubed term, so it's there. And this is the x to the 4th power, and there is our quotient, dividing x minus 1 into this polynomial. And there's the work, and there's the result. There's the x minus 1 that we're checking. There's our quotient, with a remainder of 0, of course. Small reminder over here. If we put the 1 into x, we get a 0 for y. That's what these tell us. This is the x value, that's the y value of one of the points on the graph of that polynomial. Okay, how about this one? Factor that into linear factors. In other words, x minus x plus, something like that. If x or minus 3 is a 0. Remember, x minus 3 is a 0. If you want to do this, you can say this is one of your solutions. If you get everything on one side, this will be x plus 3 equals 0. Excuse me. This is one of your linear factors. If negative 3 is a 0. How can we check that? Take that negative 3 and use synthetic division. Bring the 6 down, multiply that 6 times negative 3, there's your negative 18. Add these terms, you get a 1. 1 times negative 3 is negative 3. Add these, you get a negative 1 times negative 3 is a positive 3, and you've got a remainder of 0. So that means that our x plus 3 that we were checking to see whether it was a factor is definitely a factor, along with what? Well, this is always the remainder. The next one is the constant. So this is a negative 1. Over here, this will be an x term, so it'll be plus x. This will be an x squared term, so it'll be 6x squared. So what we have, let's bring this up here. We've got x plus 3 and 6x squared plus x minus 1. Those are the factors. Now, you can take this, factor that. So there's our quotient dividing by x plus 3. And you can factor the 6x squared plus x minus 1. Not too hard. By the way, if you're doing this by trial and error, this 1 would have to give you or come from a plus 1 here and a minus 1 there. And just see how you get the 6x squared. It could be a 6x and x, or it could be a 3x and 2x. And it probably is obvious to you that those two are going to give you the plus x you have as the middle term. Those factors are all linear. 1 2, 3, because they have x to the 1, x to the 1, x to the 1. That makes them linear factors. Now we get to something interesting. Now what this is talking about is, remember in one of the last ones we said, in fact I think it was the last one, x equals minus 3 was one of the zeros. Well, minus 3 is minus 3 over 1. That's what we're talking about with rational numbers, fractions. So if we've got a polynomial function, initially we think, oh my gosh, there are millions and millions of possibilities. There are infinite possibilities. However, by using the rational zeros theorem, we can narrow those down. Now, it might be a long list, but it's not infinite. And what we're going to look for is fractions that are zeros of that function. Now, here's the key. P, the number that's on the top, right there, that's going to be a factor of the constant term. P is related to the constant term. That's the term at the end of the function. So if we've got something like this, the constant term is there. And then we have Q, that's for the bottom. Q is a factor of the leading coefficient. So the number out here that's in front of the x, whatever it is, this is going to be a factor of Q. This will make more sense once we use an example. So here's something we can play with. Ignore the solution temporarily. This is how you get what's below. First of all, you're going to make a list of fractions, rational zeros, that are possible. Now, the ones we find aren't necessarily zeros or solutions or roots. They're possible ones, and you have to check them out. And one way of checking them out is synthetic division, which makes this a whole lot easier. So, this means that P is coming from one of the factors of 2. What are the factors of 2? Factors of 2. What divides into 2? 1 does, and 2 does. But not only that, don't forget, not only a plus 1 does, but a minus 1 does as well. Plus, minus, both of them. So we've got 4 possible numerators for rational zero possibilities, just from the constant term. Remember, these are numbers that might be in the numerator of your possible rational zero. What else? Well, this is the other one. Q. What about the number that goes on the bottom? Well, it's going to be a factor of 6. So what are the factors of 6? 1, 2, 3, and 6. Those are the numbers that divide into 6 evenly. We're talking about integers. And just as we had up here with P, it can be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. So, what does that mean? Well, let's start with the P. Let's start with the numerator and pick these out one by one. What are some possibilities? Well, the numerator might be a positive 1. So if it's a 1, what could the denominator be? Well, it could be 1, 2, 3, 6, -1, -2, -3, -6. So let's take them one by one. There's a possibility. There's another possibility using the ones. 1 over 2, -1 over 2, 1/3, -1 over 3, and 1/6, -1/6. Okay, quite a list, but remember, it's not infinite. Next, that's using a positive one. Now, how about the negative one? Well, -1, you're going to get -1 over 1. We're just changing the denominator. Well, numerator, I mean. -1 over -1, we're just changing the top. -1 over 2. -1 over -2. -1 over 3. -1 over -3. -1 over 6, and -1 over -6. Now, we're only halfway through them, but look at this. Some of these are already duplicates. For example, if you take a look at this first one, 1 over 1, that's equal to 1, of course. But down here, this one that we thought was an extra possible 0 is actually the same thing. And we only need to write it once. And this one right here, the second one, is actually the same as that one. So those 4 give us only 2 possible rational zeros. And some more of those happen. Like these are the same, these are the same. So that narrows it down quite a bit. Now, that's using the p-value. And what do we have? Let's go with the second one. That's a positive 1 and a negative 1. Now we have to work with these two. And I'm running out of room here, but let's try to squeeze this in. So let's take the positive 2. Now remember, the denominator is one of those. Several possibilities. 2 over 1, 2 over -1, 2 over 2, 2 over -2, 2 over 3, 2 over -3, 2 over 6, and 2 over -6. Now some of these, again, are ones we had before. For example, this one is the same as 1/3. So when you get all of these down, write your master list, because some of them are duplicates and you don't need to check them twice. And so that's for the 2. Now a list for the -2. Well, we end up with some of the same things. For example, -2 over 1, that's a pair of this one. We have -2 over -1, and so on. Take all those numbers, narrow them down to the ones that are distinct or unique. And here's what the final list is. Not quite as bad as it may have looked up front or up top. Now we still have 1, 2, 3, 4, 5, 6 numbers, and we can double that because it's a plus or minus on each one of them. So we've got 12 possible rational. I'm going to shorten this. Maybe I shouldn't. And the easy way to check these, if you're doing it manually, is take each one of these, like the positive one here, use synthetic division. If you get a remainder of 0, you've found the possible rational 0. Then you can check the negative one with synthetic division. See if that is a possible rational 0. Run through all those and see which ones give you possible rational zeros. Now remember, it's possible fractional zeros. And we're not talking about square roots of 3, nothing like that. It has to be a rational number, one that has an integer on the top and the bottom. So that should feel pretty good. So use the remainder theorem and show that 1 is a 0. So again, synthetic division to the rescue. We find that that gives you a remainder of 0. And so this 1 tells us that x minus 1 is a factor. And that 1 is a 0. And since all we had were rational ones, we've got a rational 0. And this is the check. That's one of the good ones. And then we can check other ones. So with that x minus 1 factored out, we can see up here what the quotient is. That's down here. That's the second factor. And then we can work with that one. Now we can use the negative 2. But notice we don't have to use the negative 2 with the original one because we've narrowed it down to 6x, oops, not there, 6x cubed plus 13x squared plus 1x minus 2. So all we need to do is use these coefficients with synthetic division and see if negative 2 is a 0. Synthetic division. Hope you're pretty comfortable with that because it is a great tool to use. So it turns out it is a 0 because the remainder is 0. So here's your next factor, 6x squared plus x minus 1, right there. So what we've got so far is we've got these linear factors, and we're at a good point. At this point, we can throw away all the possible rational zeros, and we can just factor this. Worst case scenario, you could use the quadratic formula and get the other zeros. Factoring, there we go. And of course, there's 1 0, there's another 0, and another 1, and oops, and another 1. Those are the 4 zeros. Now, is it a coincidence that there are 4 zeros? No, not really, because if you look at the original polynomial up here, it's a 4th degree polynomial. That tells you that there will be up to 4 rational zeros. And actually, we got 4. Now sometimes one of those, or 2 of them rather, might be complex numbers. In this case, all 4 of them are rational zeros. And there is a double check. There's no easy way to double check that. Probably the best way would be to multiply those two together, then multiply the result times the x plus 2, then multiply the x minus 1 times what we've got so far, and see if we end up with that. I have a sneaking suspicion you won't do that too often. That's a lot of work, but it would be a perfect check to see if you've got the right linear factors. Next, notice you could complete the work by factoring it directly. If it's not easily factorable, you could use the quadratic formula, as I mentioned, and that gives you the other two zeros without factoring. Now, this rational zero theorem only gives us possible rational zeros. Not all of those possible ones are zeros, only some of them, and you have to check them out using synthetic division. Another possibility is you could also find rational zeros if you take the original polynomial and you divide by 6. It would still give you the rational zeros. This multiplied by 6 gives you the original. Next, every function defined by a polynomial of degree 1 or more. Well, if it's a polynomial of less degree, it means what you've got is x equals 2, or rather f of x equals 2, or y equals 7, something like that. We don't need to worry about that one. We know everything about y equals 7. But if you've got a degree 1 or more, it's going to have at least one complex 0. At least. It might have more, and it might have less, but at least one. Fundamental theorem of algebra. It says if you do have a polynomial of degree 1 or more, then there's some number, we're just calling it K1, K for constant, I think in some other language, but still, K represents a constant, and this means the first constant. And there's some number, so if you put K sub 1 in your function, you end up with 0 for your y. And that says, if you find one like this, that K minus 1 is a factor. Divide it out, and you can find out what the quotient is. And you'll have another polynomial, and you can work with that, keep going round and round until you've found all the linear factors. So you can work with one by one. You start with f of x. You find x minus k1 is a factor. Then you can find x minus k2, x minus k3, and so on. So if you have degree n, that's a generic degree, could be 1, 2, 3, 4, anything really, that repeating the process, you end up with there's a factor, there's a factor, there will be n of those factors because it's degree n. You'll have n factors. And in addition to that, there will be some number that's multiplied times those. It might be a 1, it could be a 2, it could be anything really. So this is like the number of zeros theorem. If you got degree n for a polynomial, you've got n factors, or n zeros. Here you go, take a picture. Degree n, at most n distinct zeros. Now that sounds like I was wrong the first time. Not really, because you will have n zeros, but some of them might be duplicates. This means n different zeros. So for example, you might have a polynomial, and it might have zeros 1, 2, 3, 3, 4, and 7, for example. Now this would be a 6th degree polynomial, so you'd have something x to the 6th, and so on. And it has 6 zeros, but 2 of those are identical. We also say it's a multiplicity of 3's because there's more than one. So it's at least 6. In this case, it's 5. Now, how can we put some of these together? This is sort of fun because it's a little bit easier. Find the polynomial function. So you're looking for this. You're looking for that. And you want it to degree of 3. And it has the given conditions. Someone told us that zeros are -1, 2, and 4. And this is important to get the actual function. F of 1 is a 3. Now what does that mean? Remember, that means if you put 1 in for x, you get a 3 for y. So you've got an ordered pair. So what do we do? Okay, if I've got a 0 of -1, that means it's got a factor of x plus 1. If it's got a 0 of 2, that means it's got a factor of x minus 2. 0 of 4 means we've got a factor of x minus 4. There is our, let's say this is a starter function, because this isn't the exact one. It's made up something like this, but there could be a number out here. It might not be just x cubed. It might be 7x cubed or something else. And we don't know what this is yet. However, we do know that when we put 1's in for x, we'll get a 3 for y. So let's see how that works. We're going to take this expression with the a that we don't know yet. We'll put 1's in for the x's, and we'll find out, or -1 rather. No, 1, the 1 over here, sorry. We'll put the 1 in for these x's and set it equal to 3. So we're going to set this equal to 3. And we're going to find out what a is. So f of 1 is 3. That means one of the points it goes through is 1, 3. Here's our, this is the a, x plus 1, x minus 2, and x minus 4 with the -1 filled in. So what do we get? Well, we know f of 1 is 3, so there's 3, and 1 plus 1 is 2, and so on. Well, what's that give us? Simplify. We've got 3 equals 6a. Or that a, all of a sudden we know it. Because we knew this and what the zeros were, we've got the whole function. We've got the real thing. So here's our function. Here's the a, and here are the factors from the zeros that we were given. Multiply that out, and there is our function in all its glory. You want to try that again? Let's do something a little bit different. Take a look at that for a second. All right. Have you absorbed what we've got? Well, if you put together what I've mentioned earlier, you might have an idea what this first statement is about. -2 is a 0. Okay. So x plus 2 is going to be a factor, but it's a multiplicity of 3. That means this -2 is a 0 3 times. And we've got the f of -1 equals 4. Remember, before we had f of 1 equals 3, I think it was. So we can put all this together. So what do we have? First of all, we've got our function like this. This is from the -2, and it happens 3 times. And the a we don't know yet, but we know we can fix this real fast, because f of -1 is 4, which means -1, 4 is a point on the graph. So we'll put the -1 in for these x's, and we know that'll result in a 4. So here's the -1 thrown in where the x's were, and we just put this in because we don't need to write it 3 times. Simplify inside, we've got a 1, cube that, that's easy, and we've got our a. And we can put it all together. 4 times x plus 2 quantity cubed, multiply it out real carefully. This won't be too hard, and multiplying at the end by 4, it won't be bad either. So you can actually give this a try. If you don't give it a try, you probably are unlikely to remember it. All right, now a reminder that if you have f of x equals something, and there are fractions in it, if there's no equation here, if this is just the definition of the function, and we see fractions in here, we cannot clear the fractions, because if you multiply both sides by 2, for example, you'd have a different function. You'd have 2 f of x, and not the f of x that you really want. Now here are 3 rules or helpful tips you can use. Now remember, we're talking about complex numbers, and we're talking about conjugates. Remember what those are? Let's take an example. Here's one complex number. Let's call this complex number 17, okay? This complex number might be something like 6 minus 4i, okay? What's its conjugate? Actually, let's call it 0. That's better. And its conjugate, the conjugate for z would be 6 plus 4i. Look familiar now? Okay. This right here says that if you add the complex numbers c and d, and you take the conjugate of that result, you would get the same thing as if you took the conjugate of each one of those and then added them together. Get it? Here you add the complex numbers together and find the conjugate. Here you find the conjugates and then add them together, and you get the same result. Pretty nice. The second one doesn't say anything very different, really. It just means if you subtract the complex numbers and then take the conjugate, you'll get the same thing as if you take the 2 conjugates and subtract them. So that's pretty handy. Now this one is different. This says if you've got a complex number to some degree and take its conjugate. So you start with this and find the conjugate. Another way of doing the same thing is take the conjugate of the number before it was raised to a power and then take it to the power. You'll end up with the same result. So conjugate zeros theorem, we've actually mentioned this before. If you know or you're told that a plus bi is a 0, automatically then a minus bi is also a 0. One important thing is, and you probably won't run into this problem is that the a and b that I'm talking about back here are real numbers. We're not going to get into something so exotic that we'd have non-real numbers for a and b. So a plus bi, you automatically have a minus bi, and vice versa. If you're told this is a 0, then that's a 0. Now, we are not going to prove this. If you really care about this, you can go through these in the slides, but I'm going to slide right over this because you don't want to see it. Now, a reminder that here is a complex number. If it's a 0, then remember that if this is 0, the conjugate is not a 0. Let's see. Okay. If that has 1 plus I as a 0, but the conjugate is not a 0. And that's because of the real coefficients. If you have real coefficients, this will guarantee you have that. You have to have the real coefficients. As I said, you're unlikely to find unreal ones in college algebra. Moving on. We'll get there eventually. Now, we want to find a polynomial function. It's not the polynomial function like we had before. And you want to find that of least degree, having only real coefficients. We're going to pretty much assume that most of the time. And you've got zeros 3 and 2 plus I. Well, what do you know right away? Well, least degree, well, it's going to have a first degree with this one. This one adds another degree, second degree. And if you have 2 plus I, then you're going to have 2 minus I too. So it's going to be a third degree equation because you'll have these 3 zeros. So what does this look like? Well, let's take a look at this one first. We're going to build our polynomial. If 3 is a 0, then one of the factors is x minus 3. Remember that? Now, the other two are a little bit trickier because if 2 plus I is a 0, then look at this. Then x minus 2 plus I is a factor. I write this over here because we can simplify this a little bit and just write as x minus 2 minus I. There you go. And this one, of course, means that you've got a factor of x minus 2 minus I, which simplifies to x minus 2 plus I. And if you multiply all those together, you're going to get a polynomial function of least degree. It has to be third degree because you got 3 zeros. This one, and this one, that's automatic. Now, it says what's the polynomial? Well, this is the factored polynomial. If you want the polynomial, take my advice. Multiply these two together first. When you get the result, then multiply that times x minus 3. Remember, this is going to be a little bit of a long one. It's a third degree, so you might have up to 4 terms. So there are your factors down here. And we simplified them, or I did. So there are 3 factors, and those are the simplified ones that we had. these multiplied together, which I suggest to do that first. Look at that, no i's. That's why I suggested multiply those two together first, then multiply by the x minus 3. Remember, x times all of these, and then minus 3 times all of these, then simplify. And there you go. There is your polynomial of least degree. This is what you want. Now, it's not the only one. It's a polynomial function. I'm sure there's one of you that's clever enough to say, well, what about this one? And you'll write x cubed minus 7x squared plus 17x minus 15 on your paper. And just for fun, maybe you multiply all that by a -2. Well, that has zeros of 3 and 2 plus I and 2 minus I as well, and it's a little bit different. You can have a lot of these. Just change this, and you've got another one that has those qualifications. Okay, moving on. All right, we already did this. Now, how about this one? Find all zeros of this, and we know that 1 minus I is a 0. What does that tell you right off the bat? Well, if 1 minus I is a 0, then automatically 1 plus I is a 0. Now, I'm going to do this a little bit differently from what the slides do. And I'm going to leave some of the work for you. I'm sorry, you're going to have to do some of this yourself. But I'm going to show you how to do it. Now, these are zeros. So remember, that means that x minus 1 minus I that we're given up here, that's a factor because this is a 0. We also have x minus 1 plus I. Those are two factors. And our polynomial will have something else that will eventually multiply together and give us f of x. What is that, the rest of it, the g of x? Well, here's how you can do it. And here's where I'm going to leave part of it to you. The first factor we can simplify as x minus 1 plus I, right? And the next one is x minus 1 minus I. Okay. And something we don't know yet. Now, here's where I'm going to leave it in your hands. Multiply those two together and divide it into your original function. That'll give you g of x. And g of x, notice this is a 4th degree polynomial. This is going to give us a 2nd degree polynomial. So this is a 2nd degree polynomial. And you'll be able to use the quadratic formula for that one. Now, this is another way of doing it. I'm just giving you a little bit of a shortcut or a different way of doing it. Excuse me. So there's one of our factors, which I showed you up here. A little bit obscured now, but so that's a 0. Now this is the other way of doing it. And you can definitely do this. It's a good practice just going through this procedure and seeing how this actually works. If you need some practice with complex numbers, operations with complex numbers, here's your guide. So remember, bring this first number down, just copy it, multiply this 1 times that. bring the result here. Now add these two together. The real number part gives you minus 6. The complex, or the imaginary part, just minus I. And multiply this by the 1 minus I. Put the result here. Add them together. You get 11 plus 5i. Multiply that times 1 minus I. Here's the result. Add it to the negative 22, and you get this. Multiply that times the 1 minus I. Now that's going to take some extra work. You might have to use a scratch piece of paper, but do it once maybe. And multiply times the 1 minus I, you actually end up with a negative 12. Add it to the 12 that's up here, 0. So 1 minus I, as we knew, is a factor, or is a 0. Now, that gives us a really strange polynomial. Because remember, this is the constant, this is the x term, this is the x squared term, and this is the x cubed term. So this is what it looks like. Really strange, right? It's strange to me too. Don't feel too bad. Here's our first 0, written as a factor. This is what we get as the quotient. 1 plus I is also a 0. So we'll use 1 plus I with synthetic division on this to get a lower degree term. So there's our 1 plus I. Remember, we used 1 minus I before, but we've got this reduced polynomial, and we'll do that. Bring the 1 down, times the 1 plus I, and there's your result. Add them together, negative 5. Now that's pretty nice, right? Take negative 5 times the 1 plus I, and there's your answer. Add those together, 6. That looks pretty nice too. 6 times 1 plus I, there's your 6 plus 6i, add them to what's above, and you get a 0. Good work. So what do you have now? You've got those zeros that you had before, 1 plus I and 1 minus I. And here you've got 6, that's the x term, and this is the x squared term. That's your third factor. And it's a quadratic, and that means we can use the quadratic formula, or we can factor to get the other two factors. There we go. The x squared minus 5x plus 6 is ready to be factored, one way or the other. And there is f of x written in factored form. Notice it was x to the 4th, that's up here. See up here? It's a 4th degree polynomial, so we've got 4 factors because we've got 4 zeros. All right, you might want to go through this again because there's a lot of work there, but it's pretty basic. It's not too bad once you get into it. So there's our function. The other zeros were 2 and 3, of course. 2 from that, 3 from that. And there are your 4 zeros listed. Now, last of all, we're going to talk about Descartes' rule of signs. Okay, what are we talking about here? Well, we're talking about real zeros. What we want is how many of them do we have? How many do we actually have? With Descartes' rule of signs, if you were making a list of the zeros, you had 2 columns. you'd have positive zeros, and you'd have negative zeros. The Descartes rule of signs allows you to figure out pretty close how many positive zeros you have and how many negative zeros you have. Now, notice this doesn't say anything about complex ones, only the positive ones and the negative ones. Just keep that in mind. All right, so what do we have? Here's the way it goes. So what's the number of positive zeros that we can expect? Like a 2, 3, 7, 8, positive zeros. Here's the way you do it. Start at the beginning, where else would you start, and see how many times as you go down the line of the polynomial, how many times the sign changes. When we go from here to here, that's one sign change from positive to negative. Move to the next one, it changed sign again, and that's 2. Again, well, that didn't change signs, so we've still got 2, and this one changes sign, so we've got 3 changes of sign. Now, does that mean there are 3 positive zeros? No, not quite. What that means is there might be 3 positive zeros, but take this number right here, the 3, subtract 2 from it, you get a 1. That tells you there might be 1 positive zero. Sorry. So here's the number we got that says there might be 3 positive zeros. Subtract 2 from it means there might be 1 positive zero. Now subtract 2 from that, you've got a negative. You can't have a negative number of zeros. So just take this down until it bumps against 0, so to speak. So what we know now is in this polynomial, we either have 3 positive zeros, or we might have 1 positive zero. Now, if you look back here for just a moment, it's a 4th degree polynomial. If there are 3 positive zeros, there might be a negative 1. If there's only 1 positive zero, there's a possibility you could have some complex ones. But we don't care about those for Descartes' rule of signs. What we found out so far, when we talk about positive zeros, there are either 3 of them or 1 of them. Now, let's move on. Second, we're going to move on to the next slide. But I want to throw this at you so you can see them together. How about the negative zeros? We talked about positive zeros. There might be 3 of them, there might be 1. How about the negative zeros? Well, we already went through this because, and that doesn't tell us about the negative zeros. This is what we have to do. We're going to take that function and we're going to put minus x's in where the original has x's. So we'll have, where we had x to the 4th, we'll have negative x to the 4th. Minus 6, not x, but minus x, and that's cubed. Notice it parallels this. Next, positive 8, it's x squared. Now we'll make it minus x squared. And next we've got 2x, so 2, and change the x to a minus x. And a minus 1, nothing to do there. Now let's see what we've got for f of minus x. First of all, on this one, we've got x to the 4th, okay. Now on this one, you cube the minus x, that's minus x cubed, but you're taking that times a minus 6, so you have positive 6x cubed. Got that? Now next, the minus x squared is a x squared. Might make a note up here. And that's 8 in the front. So that's pretty simple. And next one, with 2 times negative x. No fancy business here. Just minus 2x. And of course, the negative 1. So we've got what we need. This is going to help us find out how many negative zeros it might be. We're going to do the same as we did before. Change of signs. So let's take a look. In going from x to the fourth to 6x to the third, sign doesn't change, 0. From 6 to 8, sign doesn't change, still 0. From 8 to negative 2, 1 sign change. From negative 2x to negative 1, doesn't change. So we still have 1. This means there's 1 negative 0. 1 negative 0. So we've got either 3 or 1 positive zeros. We've got 1 negative 0 for sure. Now, if this had been a bigger number, if this had been a 4, we'd say there's 4 negative zeros, or subtract 2 from that, 2 negative zeros. And then forget the 0. If it had been 7, it would be 7, 5, going down by 2s. Okay, 1 negative 0, nothing to subtract from that. We're already up against 0. So, what are the possibilities? Oh, they're finishing that up for us. We already did that. Let's move on here. There we go. And what do we have? For positive real zeros, it's either 3 of them or 1 of them. Remember, we subtracted 2 until we ran out of positive numbers. For the negative zeros, you have 1 change of signs. We did that. And exactly one negative real 0. Since it's a 4th degree, it has to have 4 complex zeros. Now that doesn't mean it has anything to do with imaginaries necessarily, but it's possible. Because remember, 6 is a complex number. You think it isn't? Well, this is the same as 6 plus 0i. So yes, even 6 is a complex number. But a simple complex number, I guess you could say. So we've got 4 zeros, and according to Descartes' rule of signs, exactly one of those zeros is a negative real number. We know that. So we might have 1 negative and 3 positive. And then since that covers all 4, oops. And yeah, that covers all 4. So that's 3 plus 1, that's all 4. So that takes care of the 4 zeros that we expect from 4th degree polynomial. No room for a non-real complex. But the other combination is you've got 1 negative, that's for sure, and 1 positive. That leaves 2 extra zeros. And they're not positive, they're not negative, so they're 2 non-real ones. Remember, these are the possibilities. 3 positive, 1 negative, or 1 positive, 1 negative, and then a non-real complex. And there's a little table for you. Here's when you have 3 positive, 1 negative. That covers all of them. And so there's no room for non-real complex. If you have 1 positive, 1 negative, you've got 2 others, and they have to be non-real complex. And of course, isn't that what you'd expect? Because the complex, or the non-real complexes, the ones like 6 minus 5i, they come in pairs. Remember, complex conjugates? So you'd expect an even number to be here. That's why when you subtracted 2 from 3, you got a 1. You skip the 2 because it's going to differ by 2. Because if there are any non-real ones, they're going to come in pairs. Well, that's it, folks. I hope you made it the whole way through. Good to see you again, and we'll see you again in section 4. Until then, take care of yourself.